So welcome everybody for the fifth lecture out of six of this course on Landau-Ginzburg models by John Alexander Cruz Morales from the National University of Colombia. And thank you, Alex. Your time.
Okay. Thanks, Marina, and thanks everybody for coming. Right. So today I want to discuss somehow a kind of generalization of the situation we have been discussing in the previous lectures. So let me just say in a very general, pick some kind of general setting for this uh, discussion today. So let me try some kind of general setting. So today we have a scalar manifold. Scalar manifold. We have to ask some kind of technical thing, which is not really that relevant, but okay. That is the first Betty number is not zero, right? And then again, so we can go to to the physics, and then so we can define n equal to supersymmetric field theory. Supersymmetric field theory. So the kind of theory we discussed in the first lecture. So by specifying a closed holomorphic one form, let me call it alpha on X, instead of holomorphic function so what we did before for the usual Landau-Ginzburg model was to have this function W that we'll call potential. So today, actually, what we want to do is not to consider this function, but consider as uh, uh, a closed holomorphic one form, right? And actually, when the form is exact, will say that we can recover the previous setting for the usual, let's say, Landau-Ginzburg models. So what will be actually twisted masses in this context? So in this context, so in such a case, where you have this one, this closed holomorphic one form, in such case, so twisted masses means so refers to a period interval of the form, right? The one form lambda around a circle. And we call the circle gamma in H1. It's Z. So I will actually explain that there is another source of twisted masses, and this is kind of physical motivation of the twisted masses, but I will say that actually what the what actually is the meaning of these twisted masses in mathematics. I can just say that the idea is that we can work equivalently, and these twisted masses will actually should correspond to the equivariant parameters when we actually consider the action of some group or some torus. But I will actually talk about this later today. Good. So for now, I mean, in general, the general setting is okay. We can replace. We can have this one closed form, and then you can compute these periods, and that will be the twisted masses, right? So let me make some remark is that we can recover. So we recover the case of a Landau-Ginzburg model associated to the function associated to the pair x and w when the form is an exact form, when alpha is an exact form, so being written as the okay, for this global holomorphic function Wx, global holomorphic function W of x. That's okay. So in summary, summarizing this discussion is okay. Landau-Ginzburg model with the twisted masses is just a theory defined by a closed holomorphic one form. So let me make some kind of remark that probably could be helpful. That this generalization actually is analogous to the following situation. So an analogous situation is the generalization of Morse theory. Morse theory. The so-called Morse-Novikov theory. Okay. Okay. So where instead of considering a Morse function h, okay, on a Riemannian manifold, we consider a one form. One consider close one form. Yeah. This is what is happening. So you want to see somehow this kind of discussion, you can look at the Kontsevich-Soberman paper. So see Kontsevich-Soberman. The paper is this holomorphic floor. So actually, this is the paper I sent you to the reference during the weekend. So that's somehow uh, the situation, right? So let's somehow discuss this thing in more in more detail. Okay, so let's see this generalization is with more detail. This kind of generalization, I mean, to fix what actually will be these distances. So classically, so we can make a sigma model massive. You know, with roughly speaking, see massive means so we consider the Fano situation, for example, and then you consider the, quantum cohomology of this Fano. So the quantum cohomology we expect, but for at least good type of Fano is semi-simple. So in that sense, we call somehow the theory massive. Somehow massive for me means like, the quantum cohomology will be semi-simple. So actually, at the end of this lecture today, I will discuss another semi-simple theory which is not coming from the final situation. So, but massive means like it's kind of what is the different thing. What we have the target Calabi-Yau, because when we have a Calabi-Yau, when the target is a Calabi-Yau, so the theory is not massive, but somehow we that's what. So when we have a final, that's what we have. Okay, so we can do it by the following things. So by writing down some potentials, right? It preserves the supersymmetry. Supersymmetry. They present supersymmetry. So let's see. So what kind of so there are two kind of potential we can add. So two kind of potential. Two kind of potential can be added. Okay. So the first one we know is just holomorphic. Okay. It's just a holomorphic function. Holomorphic holomorphic function. W for manifold to see. That's what we actually did before. So this is Landau-Ginzburg model. So somehow we said, okay, there is this generalization using a closed holomorphic form. So there is some generalization we already mentioned. This is kind of geometric data of a closed holomorphic form. Next, that's it. Okay, and let me mention the second one, the following thing. So we can make it this sigma model massive. Okay, let's consider a maximal subgroup, maximal abelian of the group of continuous isometries of X. Isometries the value of X. Okay, we say that is actually the rank of this group will be R. So we have some generators. So for the group, so BI will be the generators, right? I from 1 to R. So it's some holomorphic vector fields. It generates A, and they actually commute into C. Okay, so we have that. Okay, now just consider a set of complex numbers. So consider a set of complex numbers Let's call it this M with this arrow here. This M1 A MR. So somehow they are kind of, they will be somehow the twisted masses in this context. So we consider this set, so we can add twisted masses. So we can add twisted masses for A, adding the following potential, adding the potential we call it LM MRO. So absolute value for the sum one I 2R MI VR. Okay. Okay. To the bosonic part of, somehow this is the bosonic part. Okay, let me just write it completely to the bosonic part of the supersymmetric sigma model Lagrangian. And you have to do some supersymmetric completion. That's a supersymmetric completion. Okay. So the important thing is that we have two ways to somehow add twisted masses. So you can consider a one closed holomorphic form, and then you take the period. So that's a way to add twisted masses. The other thing is take the maximal average group of the isometries, and then you consider the set of the generators of this group, and somehow corresponding to these generators, so you have this set of complex numbers, and then you can cook up some potential, which is this LM, using this twisted masses, and you can just kind of somehow deform the bosonic pair, the potential for the bosonic pair with this potential, right? So the 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 question is like, okay, so you can probably add this kind of potentials at the same time. So that's something we can do. So we can add both kind of potentials. With potentials, and still obtain n equal to 2 supersymmetric field theory. Then we need the following. So provided that this alpha, the one class form, is invariant under the maximal abelian group of symmetries, right? That's the thing. So we can do this kind of thing. So this actually leads to the following. So this leads to the following. So the most general somehow classically, the most general n equal to 2 sigma model is specified by the following data. For the following data, so we need a Keller manifold. Keller manifold X. We need a set of complex numbers. And arrow 1, 2, and here, these are digit rank A. A is the maximal available subgroup of isometries, and an A invariant plus homomorphic one form of X. So that will be somehow the model, right? And so let me discuss what will be the simplest example of this, right? So the simple example, okay, of a 30 with this two things, right? For 30, where 30 were both, have a non-zero one form, non-zero one form, alpha, and a non-zero twisted mass. This non-zero is associated to some isometry. Also, isometry. Okay, so in that case, we will have the two things together, right? So twisted mass is coming from this alpha, but also with this with the symmetry, so they should be actually somehow uh, compatible actually. So is the following. So the example will be the following. So you state X, you state S C2 complex plane. Okay, here it's standard Keller metric. And just consider the following isometries. So we consider the A will be U1. U1 isometry. Actually, that rotates. So we just take this phi, this theta, or just take two complex numbers and take it to A e to the I theta V1 and E minus I theta V2. And this theta is a real number, right? So here we have one twisted mass M, so we can turn on a twisted mass M, corresponding to this isometry. Okay. Okay. So, and we can consider the U1 invariant superpotential W equal to phi1, phi2. That will be somehow the simplest situation, right? But the important thing is the following, so that actually we can generalize this situation. So we can ask, okay, what will be kind of, let's say, natural place where we can put these two potentials. So what will be, and that will be actually interesting. And I think that for the how for the hitching community, this will be interesting. That's what I plan to discuss in the last lecture. But today I will give some kind of motivation. So what will be actually? So let me write this kind of remark. So what will be the natural place to where these two potentials actually arises? So a natural place where what kind of potentials? So the main potentials coming from one class form and going for this invariant of this isomer from the maximal subgroup of the isometries, abelian subgroup of the isometries. So formula is in the context of hyperkähler geometry. It's the concept of hyperkähler geometry. Let's see what happened. So in this context, so given a continuous isometry, given a continuous hyperkähler isometry, okay, hyperkähler manifold for X. So remember that we have three complex structures here. So let's fix one. So I'm fixing a complex structure I on X. So we can write down a three homomorphic vector field. B. Okay. Generalize the isometry. Generalize the isometry. Okay. And to run the corresponding twisted masses. how to do these things. So how to do these things. So consider this omega j plus y omega k. Okay, this is the high holomorphic symplectic form on X, right? So we can add the following potential. So we can add the potential. So so we may add the potential corresponding to the class I holomorphic one form, which is this. Okay, here no, lambda will be iota b omega, this omega the symplectic form. So this iota b, this is just the operation, this is the operation that contracts a differential form with the holomorphic vector field. Vector field B. So that's the way we can construct this closed one form, right? So actually in this context, this corresponds. So this corresponds to taking the potential. By the way, sometimes today I talk about superpotential or potentials somehow the same. It's nothing special with the word super. Superpotential of the potential, okay? When we can define it, when it is defined to be the complex moment map. So to be the complex moment map. Let me just call it this. You see, it's called this. And then you have the D. So W will be iota B omega. So that's somehow the way you can actually construct the potential. And then you can uh, see what is going on with this in this hypercurrent situation, right? Okay, so again, summarizing, so we have two sources of twisted masses. So we have two sources of twisted masses. So you consider a one form with non-trivial periods. And on the other hand, you have non-trivial twisted masses. coming from the target space isometries. And somehow uses to sum the result of Hori and Buffer. It's probably coming from Hori Buffer. They are actually mirror to each other. So in certain sense, both of them are uh, somehow, the same up to mirror symmetry. So we can just consider this. That's what at the beginning, I just mentioned that the generalization is just adding a one closed form, right? And the periods will be the twisted masses because it's kind of same as, it's kind of the same up to mirror symmetry of up to mirror of this, adding this set of complex numbers coming from the isometries of the target space, right? So how we can focus on one of them and it's okay. Okay. So what we see, well, we want to discuss a context where actually this example of this Landau-Ginzburg model with twisted masses actually appear. So there is an interesting place where these examples, this Landau-Ginzburg model appear. So the context will be given by what is called, so the program, it's kind of a program by Mina Aganagich. So let me just call it this Aganagich equivariant. Equivariant Euler symmetry. There's a series of papers by Aganagich where she described this program. In fact, there is a short version. You can look at her ICM talk. It was in 2022, I think. So you can look at her ICM talk. So this is kind of short version of this of the program. So she has probably two reprints and another with some collaborators. I think in total it's like 300 pages. So that's too much. But you want to have an idea, you can see this ICM talk, right? So what is actually the context of this Aganagich equivariant mirror where actually we will find these Landau-Ginzburg models with twisted masses. So let me consider this X. Sorry, this X is a column branch. Column branch of a Quiver gauge 3D n equal 430. So if you remember when I talk about three-dimensional mirror symmetry in the first lecture. So I talk about this column branch and Higgs branch of the three-dimensional n equal 430, and that there is this symplectic duality or three-dimensional mirror symmetry between some relevant modular spaces, right? Here, actually, I start with this context, but I don't want to discuss three-dimensional mirror symmetry. So I want to construct the two-dimensional mirror symmetry. So following this Aganagich receipt, right? So that's very interesting because there should be some kind of nice relationship between this discussion I will give today and the three-dimensional mirror symmetry. And as far as I know, in this context, maybe nobody have been discussing this kind of thing. So there is this. I mentioned the first lecture, the paper by Conan Leon and his collaborator about the three-dimensional microsymmetry is microsymmetry. So some kind of relation between three-dimensional microsymmetry and two-dimensional microsymmetry. But I mean, as far as I know, they don't consider this particular situation. And of course, they don't consider this equivariant microsymmetry as I will describe here. Okay, that's the beginning, this space. You can think of it's kind of Nakajima queer variety if you want. The important thing is that this is a holomorphic symplectic variety. So X is a holomorphic symplectic variety. So in fact, it's hypercolor. We back to what I said before. So there will be somehow the natural place to consider these kind of things, right? In certain sense, or at least the mirror of these kind of things. So we have this holomorphic symplectic that's good. So Aganagish wanted to study the equivariant mirror symmetry of this. So actually, equivariant mirror symmetry has some precise meaning in the literature, coming from work of many people, for example, Telemann and Giventhal, etc. But somehow the equivariant means different thing here. So I will tell you what actually is equivariant in this setting, which is a little bit different of the usual meaning of the expression equivariant in mirror symmetry. So the let me say that so a Aganagish proposal works in two levels. Aganagish proposal, works at two levels. So it works at two levels. Okay. One level is the so-called upstairs mirror. One level is the upstairs mirror of X. And the second, oh, sorry. And the other one, the other one is the downstairs mirror of the curve X of X. So I will explain you what is the curve in a second. So, but let me just start with the upstairs mirror. So let's start with, let me just call this one. Oh, and two. So let me start with one, upstairs mirror. And why upstairs and downstairs will be, clear in a second later. Okay. Okay, so we want to construct the mirror of X. Okay, so in order to construct the mirror of X, as holomorphic symplectic manifold, symplectic variety. Okay, I have to say that this discussion will be some kind of will be kind of physical heuristic, right? To construct this mirror, right? It's convenient. It's convenient to consider the column branch, and then call it Y check of a four-dimensional theory. So actually we have this three-dimensional M4 theory was actually a quiver gauge theory. So there was some quiver uh, playing a role in the construction. So this four-dimensional theory is based on the same quiver. Okay, this is based on the same quiver. Same quiver, right? And actually, we need to consider somehow some compactify on a circle of radius RB. Why this compactification? Because you have a three-dimensional theory. Sorry, you have a four-dimensional theory. When you make this compactification in a circle, so you get um, a three-dimensional theory, right? So that's why we need to do this compactification. So we mark the circle compactification. Remember that when I'm talking here about the dimensions, I'm about talking the dimensions, for the theory, right? So for the physical theory. So the circle compactification reduce the dimension from 4 to 3. That's the thing. One thing. And the other thing, like this white check is also holomorphic symplectic. Also holomorphic symplectic. In fact, it's also hypercolor. It's also hypercolor. Okay. Again, so but we want a two-dimensional theory because we want to discuss the two-dimensional mirror symmetry. So we want to discuss a two-dimensional theory. So we make another compactification, okay? And then we get a two-dimensional sigma model with target Y check. Okay, so by further compactification, on a circle of radius on, we obtain a two-dimensional sigma model with target space by check. Right? Somehow, I mean, I don't want to discuss this here, but in the context, there is some kind of in this concept, there is this notion of multiplicative variety and additive variety, and what we are actually doing is try to play this game between somehow some multiplicative versions and additive versions of these varieties, and that will be play some role in mirror symmetry probably, and I hope I will discuss this multiplicative additive thing on Wednesday, the last lecture, because it will play some find some role in our discussion about heating systems, right? Heat. So we we have this sigma model, and actually we have that this is hypercolor. So there is this idea, this trick in microsymmetry. So since white check is also hypercolor, we also mentioned that hypercolor. We can get its mirror, y, can be obtained by hypercolor rotation. So that's it. So the natural question I think is, so the question is, okay, so what is the relationship? What is the relation between X and Y? Okay. So that's the thing, right? Because so we start with X, we want to construct the mirror of X, and we said, okay, it's kind of convenient to consider this Y check, and we actually construct the mirror of Y check. But what will be actually the relationship between X and Y in terms of a mirror symmetry? Okay, so let's see the following. So as holomorphic varieties or holomorphic symplectic varieties, so as holomorphic symplectic varieties. We have that the Y check is equal to X minus some union of divisors. So where this DB actually is the union of some divisors DB. So this is actually the difference between Y check and X, right? So if we want to compute the mirror of X, so to compute the mirror of X, to compute the mirror of X, okay? So we need to understand the mirror of partially compactifying this Y check adding the divisors, right? So to compute the mirror of X, so one needs to understand the mirror to partially compactify Y check by adding in the divisors the A check. But what actually would mean to add in divisors, you know? So in mirror symmetry, this correspond to you construct a superpotential on Y, which is actually the mirror of Y check. So we have Y check. So we want to add some divisors, we want to compactify, then adding some divisors. So in the mirror picture, correspond to construct a potential on the mirror manifold. So the addition of divisors correspond by mirror symmetry symmetry. Turning on superpotential. Let me call it W, this on Y. So actually, the mirror of X is Landau-Ginzburg model. Y is W. So we had so the actual mirror of this is a Landau-Ginzburg model, right? This is what we call the upstairs mirror. Oh, actually, again, it's called the upstairs mirror. This is the upstairs mirror. So far, no, not yet twisted masses, right? So let's see what happened with the twisted masses, right? So this is the upstairs mirror. Good. So now let's discuss the downstairs mirror. Downstairs mirror. Good. Again. So what we have to see is like you take X, this conference. So this X has a CQ star symmetry, torus symmetry. Okay. Which scales its homomorphic symplectic form. Okay. So the invariant locus with respect to this, so the invariant locus may call this straight X, sits inside curly X, it's a holomorphic Lagrangian. So this means that have the dimension of curly X, and this is called the curve. And it is called the curve of points. So we have this action, right? Scaling this the holomorphic symplectic form and invariant locus. That's the curve. So yeah, this is a Lagrangian submanifold of curly X. Okay. We also have to say that X also has a larger torus of symmetries. Has a larger torus of symmetries, right? And I will call it this torus T, and it just C star. This is the rank of G, C, Q. So what is this G? Remember that we have this equivalent gauge theory. So actually this is the Lie algebra associated to the gauge group G. This is this G here, the Lie algebra associated to the gauge group G, right? That's good. So what will be the downstairs mirror? So you have the curve. So this curve has its own mirror. So that will be the downstairs mirror. So the mirror will be the mirror of the curve. And it turns out that the mirror is again a Landau-Ginzburg model, right? It's another Landau-Ginzburg model. So the downstairs mirror is the Landau-Ginzburg model. The Landau-Ginzburg model, correct? Y W, which is the mirror of the curve X. Okay, that's the mirror of the curve X. Okay, perfect. Good. So here actually you have this superpotential. So the superpotential W. Okay. So again, it's a multi-value holomorphic function. Holomorphic function. Right. Which mirror the equivariant T action on X. So, okay, and let me write this and then we'll explain something. So, and Y is fibers over Y with holomorphic Lagrangians. Holomorphic Lagrangians. C star M fibers. So this M is because the dimension of X is equal to 2M, right? So this M, the half of the dimension, right? So that this is really interesting because somehow here we have in this, when we consider the torus action, so the equivariant parameters actually are mirrored. So the Landau-Ginzburg model we construct actually mirror this equivariant action. So the twisted masses, actually here we have a Landau, in the V model, we have a Landau-Ginzburg model with twisted masses. And the twisted masses are mirror of the equivariant parameters we get from the torus action on X. So here there is a kind of a technical and subtle thing. So, and I mean, we construct the downstairs mirror, and when you construct when we construct the upstairs mirror, we didn't consider the torus action at all. So that was not equivariant in certain sense because we don't consider somehow the torus action. But then when we want to have the complete picture, so we need to consider the torus action. So the previous curly W here, so this curly W here in the upstairs mirror, this curly W here, actually it should actually need to consider also there is there is also we need also to consider somehow the equivariant parameters. So when we consider these things, so I will actually denote with the same letter, but when we consider the torus action, this W actually changed a little bit because now we have to add some terms to correspond to the twisted masses we are turning on in this potential, right? So that's it. So adding the twisted masses in the V model actually correspond to in the A model to taking some equivariant action of, in this case, with respect to the torus, right? So that's what we have. So that's why in this context we have Landau-Ginzburg model with twisted masses. So what I'm saying is like the the mirror of these holomorphic symplectic manifolds in the organic setting, actually they are Landau-Ginzburg model with twisted masses, as we considered before, right? So, but it remains the following question. So we're gonna ask the following question. So probably it's natural. So we have two potentials, right? Curly W and the W, the usual W. So what is the relationship? What is the relation? What is the relation between this curly W and this W, right? So this W here, so the superpotential here, the W I consider is the W with twisted masses. When we already put the torus action into the picture, right? So the superpotential potential W, but I am, abusing of the notation. I am using the same W for also, denoting the superpotential with the twisted masses. So the superpotential W on Y must must satisfy, right? First thing, so when we restrict this potential, so restricting to this, so this C is some kind of local coordinates to omega to equal to zero. So we recover W and to the 10 of this curly W can be written in terms of local coordinates, sorry, globally defined coordinates on Y. So it's a little bit involved, but in Agonagis you will find a receipt of how to actually write this W with these properties and how to get these Landau-Ginzburg models, right? And as I said, so this W has some additional terms I mean, that corresponds to the action of T. So what we have is the following. So we can summarize everything in the following diagram. So we have the following diagram. So we start with this. Sorry. Okay. We start with this, the holomorphic symplectic manifold X, and we have the torus action there, right? Then we can construct the mirror, the upstairs mirror. Upstairs mirror, right? And then next mirror is this Landau-Ginzburg model of Y somehow with these twisted masses, right? So you have here this chord, which is X, the chord, right? And then you can construct the mirror of the chord with this is Y W. And you have this vibration between Y and curly Y and Y. So we have this vibration here. There's a vibration. And then the relationship between this kind of a Lagrangian vibration, right? This is a Lagrangian vibration. And the relationship between the two potentials is that you have this restriction. If you take some coordinates here, they produce W, right? And that's what we call the downstairs mirror. How upstairs because it's in the up part of the picture and downstairs because it's in the down part of the picture. So, but again, you're gonna okay, what actually will be the equivariant mirror because I haven't said anything about the equivariant mirror. So the Agaragi's proposal was, okay, if you look at the diagonal in this picture, so you can relate this thing to this thing. And that's what she called equivariant mirror. So what is the equivariant mirror of, so the equivariant mirror in Aganagi's sense, the equivariant mirror of X, and I put here T because of the action of the torus, right? Is the mirror, is the Landau-Ginzburg model mirror, sorry, the Landau-Ginzburg model mirror to the curve X of this curly X. Okay? That somehow, I mean, somehow the standard equivariant mirror symmetry will be the upstairs picture. If you consider the action and then you take this Landau-Ginzburg model with twisted masses, that will be probably the usual equivariant mirror symmetry. I mean, in more, natural sense. But this equivariant mirror in the sense of Aganagi is really strange because, in fact, X and Y, they don't have the same, they don't have the same dimension. I mean, the dimension of X is half of the dimension of curly X, right? And that will be like, it looks like very, strange things. But that's what actually she proved actually, and she did in some examples. So the theorem is the following. So this is the theorem. I think it's by Aganagish. But I think that it's convenient to take the word theorem modulo physical mathematics. I mean, I don't think it's a theorem in the mathematical sense, right? I mean, it's a theorem in the physical mathematics sense. One of the nice thing project will be to make this very precisely mathematically, because as I told you, there's a lot of physics heuristics. So to make the math correct will be a nice project, right? So what will be the theorem? So let me write the theorem. So the LG model, Y W, but the W is not the curly one, it's the W. Yeah. Which is it's a lambda visible also with twisted masses, because the equivalent part, this equivalent parameters actually mirror to the expression of W, that which should correspond to twisted masses, equivalent parameters in the A model. So the LG model is the equivariant mirror of X. Mirror of X. In the sense that the A model of X, right, computed by Gromov-Witten theory of X, working equivalently with respect to the action of T. So in fact, that this Gromov-Witten, this genus zero Gromov-Witten theory here is, so the genus zero Gromov-Witten theory actually, that was actually computed by using these ideas of Okunka, Polik, Pandaripande, and these people actually. So we actually need to work equivalently because X is non-compact. So So that's what we need to work with. Warrantly to compute the Gromov Witten, the genus zero. So in fact, they compute the quantum cohomology ring. So we know that the quantum cohomology ring very explicitly, right? So in cases of the Nakajima queer variety, this is an interesting work. So you can look at the book by Okunkov and Morik. So that's very nice piece of mathematics. This is very mathematical. So this is not physics heuristic. So this is really mathematical computation of the A model using the quantum cohomology, right? So that this A model coincides with the B model Y W, even though X and Y don't have the same dimension, right? And that's what she means by equivariant mirror symmetry. So the equivariant model here, a model here, equivariant one here correspond to the V model here. But in certain senses, it's not, this is not equivariant because this is interesting. Somehow you look at this W actually has twisted masses that corresponds to the equivariant parameters of this action. But if you look at here, when you look at the X, it's actually a usual Landau-Ginzburg mirror of X. But somehow, I mean, because X is the core of this thing, so somehow X knows some information about the torus action. But if you look at the downstairs, this is a usual Landau-Ginzburg model. I mean, you don't need to consider twisted masses or something like that. But when you look at the diagonal and you look at the relation between the X, curly X and T and Y, so you see that this W actually should be a Landau-Ginzburg model with twisted masses as we described earlier. Yet, this is still a question. So if we can write this in using this language of the 1+ form, etc. So this is not a language actually Aganagish use, but that probably that should be the right way to write these potentials and make this discussion, right? Using this generalization proposed by Greg Moore and Kahn, and also by Kolsevich and Segelman, right? There is one other interesting thing is like, okay, this is not here Fano situation, right? But this downstairs looks like kind of Fano situation, and we get that the V model here is semi-simple. And in fact, the A model is semi-simple too. So we have this semi-simplicity theory, right? So we have a semi-simple cohomological field theory. So we have this, and why this is interesting, because if you have a semi-simple cohomological field theory, if you know the genus zero theory, you know all the genera using the Giventhal Telemann reconstruction. So in fact, this theorem works not only this term does work not only in genus zero, but in all genera, because you have a semi-simple theory. So in fact, the correspondent holds in all genera. The reason why is because we have a semi-simple theory. So we can apply the Giventhal Telemann reconstruction. right? So in certain sense, the situation here when we have holomorphic symplectic manifolds, like coming from the column branches of some n equal 3, some three-dimensional n equal 4 theories. So this kind of X, I mean, the mirror symmetry picture looks like the picture for the final manifold in a certain sense, but this you can think of as a kind of generalization in the sense that somehow the mirror because we need to work equivalently. So the Landau-Ginzburg models appearing are actually this Landau-Ginzburg model with twisted masses, right? And as we expected some in Fano situations, so we get, I mean, for many Fanos, we get this semi-simple, not for every Fano, but for some manifolds, we get the semi-simple theory. So here we also have semi-simple theory, so we have everything. So we can reconstruct all general. What is the important thing is the following. So let me just say something about that. So for the Fano case, probably mentioned this. I didn't know if I mentioned, but I mentioned the Dubrovin conjecture before. So there is this conjecture that if X is Fano, right? So the quantum cohomology is semi-simple. Quantum cohomology is semi-simple. If and only if the Dirac category of coherent sheaves of X has a full exceptional collection. So this means that the Dirac category has there's a good set of generators, if you want, right? And there is other relationship that actually came from this. So this is actually proof if X is projective spaces, for example. So, okay, if X is, for example, a projective space or a Griezmannian, and in other cases for some three-fourths, etc., this conjecture have been proved. So good. So now we produce, this semi-simple theory also for this holomorphic symplectic manifold. So I want to, to finish to asking, is there any analog of the Dubrovin conjecture in this setting? So when we work with the equivariant direct category, what will be actually this is kind of this is really actually a mystery for me because you look at the level of the differential equations. So in the final, remember, but we get some equation with the quantum differential equation has two singular points, one regular point at 0, irregular point at order 2, right? And then, but here for this holomorphic symplectic manifolds, the quantum differential equation has only regular singularities. So the quantum differential equation looks more like the regularized quantum differential equation for the Fanon than for the usual. I mean, for the quantum cohomology, for the quantum differential equation, the equations in this context we get looks like more like regularized quantum differential equations for Fanos. So that I think that will be really interesting. Try to put these two frameworks, the Fano and this holomorphic symplectic, in one big context. And I think my proposal is really, kind of naive proposal. I mean, it's like, okay, maybe the right context to think this using mirror symmetry is to consider the world of the Landau-Ginzburg model with twisted masses, because in a very big, as a very big picture. And then, some part of these things correspond to somehow for the Fano story. I mean, the mirror of the Fano, and some of these correspond to the mirror of these holomorphic symplectic manifolds, right? But both of them have the main common of having part of this story of this Landau-Ginzburg model with twisted masses. That's what I actually will like to propose, right? For the next time, I want to propose another picture that somehow we can try to understand mirror symmetry for Hitchin systems, or some kind of equivariant mirror symmetry for Hitchin systems in terms of Aganagi. And I will try to describe how this picture I described today for the twisted, or this Landau-Ginzburg model with twisted masses and this Aganagi equivariant mirror symmetry should look like for Hitchin systems. Of course, I have to say that my picture is very speculative, so maybe incorrect. But I mean, anyway, I want to discuss with you because maybe we can find the right picture together. Who knows? Okay. So that's what I wanted to say for today. Thank you.
Okay, let's thanks, Alex. Okay, let me stop the recording.